Alright, let's move to a little bit more abstraction here, closer to our proof. Suppose p of x is the parent graph and f of x is the transformed graph. And suppose that c is equal to positive 2. In other words, you're taking the parent graph and you're adding 2 to the x value to reach the transformed graph. We want to find a value for x2 for our second x value, meaning our transformed function x value, such that p of x1, in other words, the original x value that I plugged in, must be equal to f of x2, the new x value that I plug into my transform function. Well, from our definition here, p of x2 is equal to f of x. So I'm going to replace f of x2 with p of x2 plus 2. In other words, if I take my parent function and I add 2 to an x value, I get the transformed function. Okay, so next we're going to treat this like an algebra problem. I want these to be the same. I want p of x1 to be equal to p of x2 plus 2 so I can get the same y value back. So I'm going to set x1 equal to x2 plus 2. So if x1 is equal to x2 plus 2, that will ensure that p of x1 is equal to p of x2 plus 2. So now that I've established that, I'm going to set x1 equal to x2 plus 2. I'm going to subtract 2 from both sides. Again, you can see why this is why when c is equal to positive 2, I have a shift to the left of 2 units because I have to subtract 2 from both sides. And now I get x1 minus 2 is equal to x2. In other words, my original x value, if I subtract 2 from that, that will give me the new x value that I need, the x value that I need for my transform function. And this all has to do with algebra. I'm subtracting 2 to compensate for the original plus 2 value for c. Okay, so let's review. So when x1 minus 2 is equal to x2, this will ensure, well, let's see what happens. So when p of x and p of x plus 2 is equal to f of x, what happens? Well, if p of x plus 2 is equal to f of x, then p of x2 plus 2 is equal to f of x plus 2. Right there, we're just substituting x2 in for x. Again, we're getting closer and closer to a formal proof of why this happens. So we have p of but we've established that x1 minus 2 is equal to x2. So let's replace x2 with x1 minus 2. Now we're going to see why it works. Now we're going to see that our minus 2 and plus 2 cancels, and we have p of x1 is equal to f of x2. In other words, the y value for my initial x value is equal to the same y value for my new x value. In other words, when we look at this example we had here, p of x1 would be equal to 9, right? And then f of x2, in other words, f of 1 is also equal to 9. It's the same thing happening graphically as with our proof. And therefore, we've proven that p of x1 is equal to f of x2 whenever x1 minus 2 is equal to x2. In other words, you're subtracting 2 from your original x value. 3 minus 2 is equal to 1 to give you the same y value of 9. Let's look at what this looks like on a chart. And this is what we're getting at because we want to be able to graph transform functions. So p of x is equal to x squared. We've looked at our parent functions already. These are the 5x values that we normally use because they're centered around 0. Negative 2 squared is 4, negative 1 squared is 1, and so on and so forth. So notice what happens if we wanted to graph f of x equals x plus 2 squared. The reality is we don't want to just plug in the same x values in because we're not going to have a graph that is centered around the origin, especially if this is like plus 100. If we plugged in negative 2, we get 98 squared, which is just insane. We want to be able to look back at a parent function and see how it changed over time. So in order to do that, we can just subtract 2 from our original x values, and that's what we're getting at. So if we take negative 2 and subtract 2, we get negative 4 back. That will give us the x value that we need to ensure that we get the same y value back. In other words, negative 4 plus 2 is negative 2. Negative 2 squared is 4. Negative 1 minus 2 is negative 3. That one give us the x value we need to ensure we have the same y value. 0 minus 2 is negative 2, 1 minus 2 is negative 1, and 2 minus 2 is 0. Okay, so don't overcomplicate this. Here's the simple fact of the matter. Whenever you add 2 to an x value, you're going to do the opposite of what you intuitively think would happen. You're going to take your original x values from your parent function, and instead of adding 2, you're going to subtract 2 from them to compensate in order to end up with the same y value. So just subtract 2 from those parent x values, and those will give you your new transformed x values, your x2 values, that will ensure you end up with the same y values. You can take any of these values and plug them into the transform function, and you'll see that indeed they give you the same y value. So now here is our new chart for our transformed function. We've subtracted 2 from our original x values. Now we have negative 4, negative 3, negative 2, negative 1, 0, and we have the same y values that we started with for our parent function. What does this look like in general? Well, in general, let's say it's not x squared. Let's say it's any parent function. Here's our original x values that we normally use. Now again, we stray from those sometimes. We might use 0, 1, 4, 9 for square root, and different x values for trig functions. But at any rate, we're going to have some y value for our parent function when we plug in these x values. So the point that we're trying to get at is whenever you add 2 to these x values to get a transform function, you want to ultimately subtract 2 to get your new x value. In other words, take your original x value, subtract 2 from it. I had plus 2 there, I had to change it. Subtract 2 from it to get your new x value. Again, it's counterintuitive, but whenever you see a plus 2 here, think about it this way. Algebraically, you're going to have to subtract 2 from your original x values in order to cancel out that plus 2 and end up with the same y value. So, take these x values, subtract 2 from them, and now you have negative 4, negative 3, negative 2, negative 1, 0, and that will ensure that you have your same parent y values as when you plugged in these original x values. So here's your new transformed, in general, this is your new transformed chart. You've taken your original x values and you subtracted 2 from them to compensate for the plus 2 that you have in front of your x. So in other words, the plus 2 minus 2 will cancel and you end up with the original parent y values. That's going to be it for this video. Next we'll look at what happens when we change this to maybe plus 3, plus 4, plus 5. You can imagine what's going to happen. You're going to have to compensate by doing the opposite. In other words, minus 3, minus 4, minus 5. If you have any other questions about this video, let me know.